So far, we've been assuming that gases behave ideally. In other words, they obey the gas laws under all conditions of temperature and pressure. But do ideal gases actually exist? The answer is no, but it makes the math a lot easier and it's a pretty close approximation to what's going on. So why not? Why don't ideal gases really exist? Well, according to the kinetic molecular theory of gases, we said that particles have no volume. That, of course, is wrong. Of course they have a volume, or else they wouldn't be there. It's just that they're really, really small compared to the overall volume of the space that the gas takes up. So we tend to ignore them to make the math work a little easier. We also assumed, according to the kinetic molecular theory, that there was no attractive forces between gas particles. And that, of course, is also wrong, too. If this was the case, gases would always stay a gas. One gas particle would never be attracted enough to another gas particle to create an intermolecular force of attraction, which would cause the condensation from a gas to a liquid. And we know that you can turn a gas into a liquid through condensation. So there are no gases for which this is true. However, a real gas will behave most like an ideal gas under two conditions, and you need to know these conditions. One is under really high temperature, and the other is really low pressure. So let's talk about these. Um, the main idea, though, is that because under these conditions, high temperature and low pressure, a gas will stay a gas. So ideal gases don't exist because molecules do take up space. These are my gas molecules in red here, and of course they take up space. They're really small compared to the volume of space that they may be in, but they do take up some space. And there are attractive forces between gas particles. Otherwise, they would never condense down into a liquid. So real gases behave like ideal gases when the molecules are really far apart from one another. This is at really low pressure. So under high pressure, these gas particles in my chamber here are really close together. And the volume of space that they take up compared to the overall volume of the container in this kind of squashed down position here is large. There's a lot of blue spheres here compared to the overall space. But at low pressure, if I increase the size of my container here, I'm now at large volume and we can spread out the gas particles. If we spread out the particles, we can ignore the particle volume a little bit more. Now the overall space of this container compared to the space that the gas particles take up is much, much bigger. So we can ignore that condition of the kinetic molecular theory that the particles have no volume at low pressures. Also, they're really far apart, so any intermolecular forces of attraction that want to stick them together are less likely to be felt when they are being spread out like this. Real gases behave like ideal gases when the molecules are moving really, really fast, and this is at high temperature. When the gas molecules are at high temperature, the collisions are harder and faster. And when the particles are moving past one another, they're doing so really, really fast. A good analogy of this is if you ever played with like refrigerator magnets, when you get them close to one another, you can feel that magnetic force of attraction wanting to stick them together. But if you took a magnet and threw it past the other magnet, chances are it's probably not going to stick together because they're not next to each other long enough for that force of attraction to stick the two magnets together. The same thing is going on with gases moving fast in a reaction chamber. The faster they move, the harder they collide, and the faster they fly past one another, so those intermolecular forces of attraction can be ignored. So in summary here, there's no such thing as an ideal gas. Real gases behave like ideal gases under two conditions. You need to know these conditions and be able to pick them out under a lineup of a multiple choice question of highest temperature and lowest pressure. At these conditions, a gas is likely to stay a gas, and that's what an ideal gas does. It stays a gas always. And although there's no such thing under high temperatures and low pressures, obviously they're most likely going to stay a gas for longer.